Hello students, today we are going to discuss a very important topic which is frequently asked in JEE and NEET exam, and that is calculation of effective resistance. Friends, in every JEE and NEET exam, if you see the paper, you will get at least one or two examples, one or two problems which are based on complex network, and you have to find the effective resistance between any two given points. So today I am going to discuss three or four methods. With the help of that, you can reduce your complex network in a simple network, and then you can find the effective resistance. Today we are going to discuss this four methods. With the help of that, you can find the effective resistance. In next video, I'll give you another three or four methods. With the help of that, you can find the effective resistance between any two given points. Let us start with our first method, which is known as method of successive reduction. Friends, if you see the name, you will come to know that what is the method of successive reduction. Here the word reduction says that from a complex network you have to reduce the number of resistors, and then you try to make that complex network and try to convert that in a simple network. Okay, what we have to do is consider this complex network. Now if I tell you that you have to find the effective resistance between point M and N, between this point M and N, what is the effective resistance? Rmn. What can be the value of Rmn? In this case, what we have to do is we have to reduce the number of resistors. How to reduce? Okay, starting from point M, consider this resistance R. Now this MR and RQ. So these two resistors are in series. You know series and parallel combination very well. So I am not going to explain what is series connection, what is the parallel connection, and how to find the equivalent resistance of a given two series or given two parallel resistors. I think you must be knowing that. So now this MR and RQ, these two resistors are in series. So what we can do is, instead of these two resistors, we can put one resistor whose value is 2R, because R plus R in series we have to directly add. So instead of these two resistors, what we can do is you can put one resistor whose resistance is 2R. So let us redraw the network. Suppose point M and point N. Now between this point M and Q, earlier there were two resistors R and R. So what I will do is, here point Q is already available, but this 2R is already there, but instead of these two resistors I will put this 2R. This 2R is a resultant of QR and RM. Okay, remaining network QP. So let us say between Q and P you are given R resistance. Now P and M 2R. So between P and M you are given 2R resistance. P and O, R, O and M, again 2R, O N, R and M 2R. So now between this point Q and M you are given two resistance 2R and 2R which are in parallel. Okay, this 2R and this 2R in parallel. So instead of this 2R I can write R, because you know that if two resistors are in parallel and their value is same, then resultant resistance will be half. So how you can reduce this? Instead of this you can write here 2R. Okay, now between point Q and M this 2R resistance, between this point Q and M this 2R resistance is given. These two are in parallel, So instead of this two resistance, I can put one resistor whose resistance is R. So what I'll do is reduce this, and value of resultant resistor is R. Now MQQP. So this resistor R and this R, these two are in series. So instead of this two resistance, I can write one resistor whose resistance is 2R. So again I am reducing the number of resistors. So instead of this two, I can put one resistor whose resistance is 2R. Okay. Come back to point P and M. Now this resistor is between point P and M. This resistor is also between P and M, and these two are in parallel. Again the same rule, if two resistors of same value are in parallel, then resultant will be half. So 2R and 2R in parallel, so resultant will be only half, means R. Okay, so value will be R. So what I am doing is one by one I am reducing the number of resistors. Okay, now come to this point PQ and QO. So these two resistors are in series. These two resistors are in series. So R plus R means 2R. Okay. So instead of these two resistors, what I can do is I can put only one resistor. So I am reducing this 2 to 1. So this is 2R. Okay. Again same thing will happen. Consider point O and point M. This 2R resistor is between point O and M, and this 2R resistor is also between point O and M. Okay, so these two are in parallel and they are of same value. What is the rule? If two resistors of same value are in parallel, in that case the resultant will be half. So 2R and 2R, you can say the resultant will be only R. Okay, so this is R. Now consider this point M and O. So this resistor R is between M and O, and this R, O and N. It means these two are in series. So instead of this two resistor, what I can do is I can put one resistor whose resistance is 2R. So let us reduce the number of resistors. Consider this is 2R. Okay. Now last step. What is the effective resistance between M and N? Now this R is between M and N. This 2R is also between M and N. They are in parallel, but this time they are not of same value. The value is different. So what I can do is 1 upon R Mn is equal to 1 upon 2R plus 1 upon R. What I'll get is, take LCM, 2R, here it is 1 plus 2, it means 3 upon 2R, that is 1 upon Rmn. So the final value will be 2R by 3. If you check the answer is 2R by 3. It is not given here. Yes, it is given. It is 2R by 3. So this is how you can reduce the number of resistor and you can find the resultant or equivalent resistance between any two given points. Okay. What I'll do is I'll give you one more example on this particular method, so it will be very clear to you. Now instead of R, let us take one example in which the perfect value is given. Consider one network which is between A and B. Okay, 3 ohm resistance is given between A and B. Now we have another 1, 2, 3, 4 points. Consider 1, 2, 3, 4 points. Okay, say it is C, D, E, and F. Now between B and C, 3 ohm resistance is given between B and C. Okay. Now C and D, another 3 ohm resistance is given. D and E, same thing, 3 ohm. E and F, 3 ohm. F and A, again 3 ohm. Okay. So this is how it is given. But from A to C, here we are given 6 ohm resistance, then 6 ohm over here, 6 ohm, and another 6 ohm. What you have to find is what is the effective resistance R between points A and B. So in such problem we can use the method of successive reduction. We have to find the equivalent resistance between A and B. So what I'll do is I'll start from this point, A to F and F to E. These two resistance are in series, means instead of this 2 I can put one resistor whose resistance is 3 plus 3 means 6. So how to reduce this? Instead of this 2, put one resistor of 6 ohm. Now consider point E and point A. Between these 2 points E and A, you will get two resistors 6 ohm and 6 ohm, and these two are in parallel. Again the same rule will apply. If two resistors are in parallel and they are of same value, then resultant resistance will be half, means 6 and 6. So resultant will be 3. So I'll reduce this network and this is 3. Okay. Consider point A and point E and point D. So 3 ohm and 3 ohm. This time, this 3 ohm resistors are in series, means instead of these two resistors, I can put one resistor whose resistance is 3 plus 3 means 6. Yes. So I'm reducing the network and I'll get one resistor whose resistance is 6 ohm. Now consider this point A and D. So there are two resistors connected in parallel, 1 and 2. They are in parallel. What is the rule? If two resistors are in parallel and they have the same value, in that case, resultant will be half. So instead of these two resistors, what I can do is I can write 3 ohm over here. You can see that I am reducing the number of resistors. Point A and D, point B and C, 3 and 3, these two are in series. So instead of this 2, I can write 6 ohm. What I can write? 6 ohm. So this is 6 ohm. Same. Point A and C, these two resistors of 6 ohm are in parallel. So resultant will be 3 ohm. So instead of this 2, I put only one resistor of 3 ohm. Again, consider point A and C and D, 3 and 3 are series. So instead of these two resistors, I can put one resistor whose resistance is 6 ohm. Okay. What you have to find is the effective resistance between A and B, means this 3 ohm and 6 ohm are in parallel and you have to find the equivalent resistance of these two. Now these two are not of same value. So what we can do is 1 upon RAB is equal to 1 upon 6 plus 1 upon 3. Take LCM, 6 here 1 and here you have to multiply with 2. So it is 3 by 6 means 1 upon 2. So your answer RAB will be 2 ohm. So if you check the answer, so answer is 2 ohm. So this is how you can use method of successive reduction from a given complex network. You can successively reduce the number of resistors and finally you can get the equivalent resistance between any two given points. Okay, so as I mentioned, in next video we will see the another three tricks and we will further go on. Thank you.